Hello everyone. Today we are going to solve some questions regarding chapter 2. So let us start. In example 1, we see a circuit composed of parallel connection of 3 circuit elements. We have one independent voltage source with a value of IV over 4. We have one independent voltage source with a terminal voltage value of Vg, and we have an independent current source which has a value of 8 amps. So for the circuit, what value of Vg is required in order for the interconnection to be valid? As you can see, we have a parallel connection of 2 voltage sources. Whether they are dependent or independent, we know that there are certain rules for parallel connection enforced by the theory, circuit theory. And in part B, for this value of Vg, find the power associated with the 8 amps source. So first of all, we know that the independent voltage source will enforce the voltage Vg across both the 8 amps independent current source and IB over 4 dependent voltage source. So I can simply write down the fact that the Vg will be here and here as well, okay, because the polarities are the same, so I can write this. And another information that I have is IB, my control current, that this is the controlling current for dependent voltage source, is chosen in this particular direction. And if you look, there is the independent current source flowing in this direction as 8 amps, but it's opposing the chosen direction. As a result, I can conclude that IB shall have the value of minus 8 amps, okay? Because of the chosen direction, I can write this to rectify stuff. And I know that the voltage across the dependent voltage source depends on this value. So this should be equal to the Vg so that I can connect them in parallel. Otherwise, this would violate the the rules of the circuit theory that we have learned. In order to connect voltage sources in parallel, we have to make sure that they have the same voltage value across their terminals. As a result, I can write this IB over 4 equals to Vg. This is a correct assumption so that the interconnection can be valid. Now in this case, since the Vg equals to IB over 4, and I know the IB value from here, I can simply plug in. It's gonna be minus 8 over 4, which would give me minus 2 volts. So I have found a negative voltage, which means that the voltage is in the opposite direction that when compared to my chosen reference direction. So it means that the voltage Vg is equals to, sorry about that, the Vg is equals to minus 2 volts. So it means that the true direction is like plus and minus 2 volts. They are the same thing, okay? Vg equals to minus 2 volts, or if I rewrite or reconnect the element like this, they represent the same thing mathematically, okay? So I have found the Vg. So this concludes part A, okay? This is part A. And for the part B, like in order to find the power related with the 8 amps current source, we need to find the voltage drop across the current source. As in the beginning of the question, it shall have a voltage value of the Vg, okay? So the current source should have the value of VG, which is minus 2 volts. Okay. Now I have accepted this as its polarity. I didn't know that its absolute value, so I just took it in this way. So the current shall flow from positive to negative, and the current is flowing in that direction. So I can take the current value as 8 amps because it's in line with my selected direction. So in this case, I can calculate the power of the independent current source as voltage across the current source times the current it provides, which means minus 2 times 8, and that would give me minus 16 watts. Okay. Now the value of the power is negative, which means that it's a source. Okay, it's sourcing energy to the rest of the circuitry. Okay, the current source generates 16 watts of power to the rest of the circuit. Okay. Now we can continue with our next examples. In example 2, we do have a circuit, a very basic circuit, a voltage source connected in parallel with a resistor. If the VG is 1000 volts and IG is given as 5 milliamps, find the value of R and the power absorbed by the resistor. In part B, if the same IG equals to 75 milliamps and the power delivered by the voltage source is 3 watts, find VGR and the power absorbed by the resistor. And in part C, if R is 300 ohms and the power absorbed by R is equals to the 480 milliwatts, find IG and VG. Now, in part A, let us try to determine the reference directions first. Like I have an IG given to me, so it's flowing in this direction, as you can see. This is the IG, this is the IR, okay, the current of the resistor, and it makes sense to choose this direction as the current is flowing in. There is no other component, so the current flows from higher voltage to lower voltage level. So I can denote the voltage across the resistor like this, and the current shall follow. So in this case, I realize that IR should be equal to IG because there is no other path for current to flow. And since I also have the resistor connected in parallel with the independent voltage source, and that independent voltage source sets the voltage across the resistor, then we can easily write this. Okay. Now, in part A, we are given VG is given as 1 kV and IG is given as 5 milliamps. Now, from what we have discovered, the VG equals to VR and IG equals to IR. And we know the terminal equation of a resistor, which tells us basically it's the Ohm's law, as all you have learned, IR times R. Okay. So since I know the VR and the IR, I can easily calculate the unknown value R, which is VR over IR. If I plug in, substitute the values that I know, 1 kilovolts is 1000 volts, okay, over 5 milliamps is 0.005. That would give me 200,000 ohms, which is equal to the 200 kilo ohms. So we have calculated the resistor value, but we are not finished yet. The question also asks us about the power absorbed by the resistor. Since I know the voltage and the current through the resistor, I can actually easily calculate it. PR equals to VR times the IR, then it's gonna be 1 kilovolts times 5 milliamps. Now this K and milli cancel each other, okay? So I end up with 5 watts of dissipated power, and the resistor value is calculated as 200 kilo ohms. Now if we go into part B, now we are given the fact that the IG is 75 milliamps and the power delivered by the voltage source is 3 watts, but we know that this voltage source is sourcing energy to the rest of the circuitry. So in this case, our PG value should be negative 3 watts because it's sourcing energy and we know it. So from here I can easily calculate the VG because the PG should be equal to VG times IG. I know these two values. So and I also, please note that the IG is chosen in the opposite direction when you compare it with the voltage across the terminals of the independent source. So the IG value is also a negative value for us, okay? It's minus 75 milliamps circuit theory wise. Because as you can see here, I'm looking the voltage across the terminals like this, but the current is flowing outwards to the source, which requires that IG should have a negative value, and I have to write it. So the overall PG is also, the negative. Then from here I can calculate the VG as the PG over IG. That's gonna be minus 3 watts over minus 75 amps, which would give me 40 volts. So I have calculated the value of the VG. Now we are also supposed to find the R. Since the circuit topology hasn't changed, the previous equations still hold. So the voltage across the resistor value should be equal to the VG. From here I know that the VR should be equal to VG, and that's 40 volts, okay? And this should also be equal to the IR times R, and I know that IR equals to IG. This equation still holds because circuit topology hasn't changed and I haven't changed my reference directions. Everything is consistent. So I know that this is gonna be 75 milliamps. From here I can calculate the R value as 40 over 75 milliamps, and that would translate into 533.3 ohms. Okay, this is the resistor value. Since I know the VG and the VR and the IR, I can easily calculate the power. PR should be VR times IR, which would give me 40 volts times 75 milliamps. That's gonna be positive 3 watts. So I can simply make sure that the total power dissipated in the circuit is Pg minus PR, which is minus 3 watts plus 3 watts, and this is equals to 0 watts. So this is kind of a sanity check. One part of the circuit is providing minus 3 watts, and the other part of the circuitry is consuming that as 3 watts. So in total we have 0 watts. Now in part C, if the R is given as 300 ohms and the power absorbed by the resistor is 480 milliwatts, then find the Ig and Vg. Now the first thing is we need to calculate the value of current and voltage across the resistor, and we know the relationship of power for a resistor. We know that PR equals to VR times IR, which is also equals to I squared R times R. That's also equals to the VR square over R. So knowing these simple fact, I can simply pull in order to calculate the current. I can say that the power can be used to calculate the current value, like the power values that we know. So I simply put this into my equation, 480 milliwatts over the 300 ohms. That would give me, now which will translate into 40 milliamps. Okay, and from the power we can easily calculate the VR. VR equals to PR over IR. That's going to be 4 over 40 that would give us 12 volts. Let us continue with the next question. So in example 3, we are given a circuit which we have a current source, independent current source, connected in series with a conductance, which is the reciprocal of resistance. Okay, so if Ig is 0.5 amps and G is given as 50 millisiemens, find Vg and the power delivered by the current source. If Vg is 15 volts and the power delivered to the conductor is 9 watts, find the conductance G and the source current Ig. If G is 200 microsiemens and the power delivered to the conductance is 8 watts, find the Ig and Vg. Okay, let us remember, when we have an independent current source, we only know its current value, which is 0.5 amps for solution. So for the part of solution. So this is the current value that I can know, and this current is flowing towards my conductance, and there is some voltage, reference voltage, given like this. Since their connection is like this, the same voltage should appear across the terminals of the independent current source. So I have to write it like this, okay, plus minus Vg. But I don't know this value. The only thing that is certain is 0.5 amps, which is given to us by the question. So we know that the Ig is given as 0.5 amps, and we have a conductance G, which is 1 over R. So I know that the Ohm's law for this conductance can be written like Ig equals to G times Vg. Okay, so this G value is given to me as 50 millisiemens. Okay, so I know the Ig, I know the conductance, then I can calculate the Vg value, right? From here, the unknown thing is Vg, so I can calculate it as Ig over G, which is 0.5 over 50 millisiemens. So I simply write it like this, and that will give me 10 volts. Okay, so now I have found Vg as 10 volts. Okay, then I also know the same voltages across the independent current source, which means that Vi, however, there is one difference. If you take a look at the reference direction of the current source, it's towards this upwards, which dictates that the lower terminal should be more positive than the upper terminal. But since the Vg is given like this and we have found a positive value, which means that our assumption for the reference direction is correct, which gives us 10 volts across this. Okay, then Vi should be equal to the minus Vg. Okay, because here I have a current source like this, so the actual value should be like this. However, my given reference, the reference that I have calculated is like this. So because of this ambiguity, not the ambiguity, but because of this positive polarity change, I have to apply a negative sign. So in this case, the voltage across the independent current source should be minus 10 volts. Okay, now I know the voltage and I know the current, so I can also calculate the power of the current source, which is Vi times II. That's gonna be minus 10 times 0.5. That's going to be minus 5 watts. Since it's a source, the power associated with it should be negative, and as you can see, I obtained this negative value across using the voltage versus current relationship within the independent current source. Okay, we know that this is 0.5 amps. And that's all for part A. In part B, we can find the value of the conductance from the given parameters. Okay, so if you rewrite the power formula for the conductance, you will see that it's going to be G times Vg square. So from here I can easily calculate the conductance value as Pg over Vg square. I know that the Pg is given to me as 9 watts and the Vg is 15 volts, so I will have to take the square of it. And if we do the math, we are going to get 0.04 Siemens, which is basically 40 millisiemens if we rewrite. Okay, so we have found the conductance. Now I can also find the current that's being sourced, because if the conductance is 40 millisiemens, and since I know the voltage across the conductance, I can also calculate the Ig, which should be equal to the current source current. So in this case, I'm going to multiply my conductance with Vg, and then 40 milli times 15 would give me 0.6 amps or 600 milliamps. In part C, if the G is 200 microsiemens and we know the power, then we are asked to calculate the Ig and Vg. First of all, I can use the same formula, like the power of the conductor is going to be conductance times Vg square, and from here I can find the Vg as the square root of Pg over G. Okay, since I know my Pg as 8 watts, and also the 200, since micro is 10 to the minus 6. Okay, this is micro. If we do the math, then we are going to get 40 10 to the 3 square root of it. Okay, then we are going to get 200 volts out of this as the Vg value, and I can still use the same formula I used in part B. Ig equals to G times Vg. Since I know that the G is 200 times 10 to the minus 6 times 200 volts. Okay, which will give me 0.04 amps, and that equals to 40 milliamps. And I can also multiply this value with the voltage to see that the power is 8 watts. So in order to check myself, I can do this sanity check automatically. Okay, let's move on with the next example. So in example 4, we have a circuit given, and for this circuit we are supposed to calculate I5, V1, V2, V5, and the power delivered by the 24 volt source. We have one independent voltage source, and we have a big loop that consists of 3 circuit elements, 3 resistors. So in this particular case, we can actually easily start using KVL, because when we have a loop, we are given certain predetermined or pre-selected references. Okay, we don't care if they're absolutely correct or not. The important thing is being consistent. Okay, now if I go clockwise within the loop, I can simply create this current path consistent with I5. Okay, I know that all the current in this loop will follow, like then I will have these I2, because the current shall flow from plus to minus, so I have a higher potential here. And here in I1, again, I1 is flowing in this direction, okay, which is opposing I5, but it doesn't really matter, because from the KVL we will get always the correct equation. And if you look at the current in the voltage source, it should be like this. Okay, sorry, since I'm always, by definition taking the correct direction as from plus to minus, I can also write it down this way. In this case, I'm going to get a negative, value for the voltage source current. Okay, which means that it's flowing in the opposite direction that I have chosen. So, if we simply write down a KVL equation clockwise, okay, I can write a KVL. So I have the voltage source, but I'm rotating in the opposite direction. As you see, I'm rotating clockwise, so I'm opposing it. I see the first negative terminal, so minus voltage source. Okay, then I come to this resistor, which is R2, let's say, okay, because it's denoted with the index of 2. So since I see the positive terminal first, I'm going to write it as a positive, and I2 times R2. This is the voltage drop across this, resistor, which is actually plus V2, as you can see. Then I will continue and come to the R5. Here, since I see the positive sign first, I just put it here, and then I have the I5 times R5, because this is how we define the positive V5. Okay. Then when I come to the R1, I see that I approach the component from the negative terminal, which means that I should put a negative sign there. Okay. And then it's going to be I1 times R1, which is minus V1. And I complete the loop. I came to the point where I started. Okay, I started with the negative terminal of this, voltage source, and I made my loop and ended up with there. So, as the KVL suggests, all the voltages within a loop or a mesh should be equal to 0. So I equated them to 0. So I have certain numerical values given to me, so I can simply substitute them in equation. Let's say this equation 1. Then I can simply write down minus 24, okay, plus 3I2 plus 7I5 minus 2I1 equals to 0. I still have 3 unknowns, as you can see. Okay. In this particular case, we can also use the KCL at the circuit nodes. Okay, I have 2 nodes here, and the current flowing into this node should be equal, like all the currents summed up at this particular circuit node, and there's another circuit node here. Okay, here I have the source current, and I have the I2. Okay, I have the I2 here at this next circuit node, and here I have the I5, and again I have the I5 here, and I have the I1. Let's say this is point A, this is point B, and this is point C. Okay. You can also write at point D, this is I source, this is I source, and this is I1. Okay. If you write down the KCL at different nodes, for instance at A, the total current should be 0. Okay, so since the I source is leaving the node, it's gonna be a positive value. Okay, from here I say I source plus I2 should be 0. And at B, same rule applies. Since the current is entering into node B, it will have a negative sign, okay, by definition. Minus I2, and I5 is leaving, plus I5 should be 0. And at circuit node C, minus I5 minus I1 should be 0. And at circuit node D, minus I source plus I1 should be 0. Okay. Now, the first, from here, I can see that I need to bring all my unknown into one unknown so that I can solve the circuitry. And there are these equations coming from KCL actually will help me to transform this set of equations into a solvable one. So from node A, I will get, oops, sorry about this, I will get I2 equals to minus I5 from the node B. I will get I2 equals to I5. Sorry about this, like the first equation is IS, not 5. I made a mistake. This is the S, not the 5. At node B, I get I2 equals to I5, and at node C, I get I1 equals to minus I5, and so at node D, I get the I1 as minus, or I1 equals to IS, which will make minus I2. Now, if I go into this, equation 1, I can simply substitute these values inside the equation and rewrite the equation like this. Okay, minus 24 volts plus. Now, instead of I2, I can write I5, 3I5, plus the I have 7I5, so I don't have to deal with it. Okay. Then I will also going to use my equations in the last part. I know that I1 equals to minus I5. If I substitute here, it's going to be plus 2I5, and that's going to be 0. Now, the only unknown is I5. Okay, I can solve this equation easily. Then I can find the I5 as 24 over 12, which equals to 2 amps. Since I have solved I5, I can easily calculate the other current values using the equations of KCL. So I know that I2 equals to I5, so that's going to be again equals to the I2, and that will be equal to the minus I1, and we can also calculate the you know, IS. Okay. Since the I2 is also equals to the minus IS, I can easily write down this like this. Okay. So you can pull all the, you know, currents out of it. For part B, we are asked to calculate the, you know, V1. It's easy once we know the current value. V1 equals to the I1 times R1, which is 2 ohms basically, and we know that the I1 is going to be minus 2 amps, and from here minus 2 times 2 would give us minus 4 volts. Okay. In part C, the same applies for, let's say, voltage 2. For the V2, I'm going to calculate the voltage drop as I2 times R2, and since the I2 is 2 amps from here, as we can see, I know that this is gonna be 2 amps and R2 is given as 3 ohms. Then I'm going to get 2 times 3, which is 6 volts. Okay. Oops, sorry about this. And for part D, V5 equals to I5 times R5, and I know that the I5 equals to I2. I already found it, so it's 2 amps, and this is 7 ohms. So 2 times 7 is 14 volts. So I can do a sanity check to see if I'm correct. I can use equation 1. I can simply plug these values into the equation and check if my original assumption was correct. Minus 40 plus the V2 is 6 volts, plus the V5, which is 14 volts, and minus V1, which is you know, 4 volts, would give us a 0 volt. So the KVL holds. Okay, which means that we have correctly calculated the voltage values and our current values are, you know, correct. And in part E, the power delivered by the 24 volt source, here V source is given as 24 volts, and IS is calculated as minus 2 amps, as you can see from the this you know, result. So the power source, the power consumption of the voltage source should be Vs times Is, and that's going to be 24 times minus 2, which would give me minus 48 watts. Let us continue with the next question. In example 5, we are given a circuit, and we are supposed to use Ohm's law and Kirchhoff's laws to find the unknown value of R in the given circuit. You have given some, you know, information here. We have 120 volts voltage measured across the 24 ohms resistance, which also gives us some idea about the, you know, voltage value, or the current value through the, you know, resistor, which should be in this direction. Okay, because it's more positive on the upper terminal. Okay, I can arbitrarily choose a voltage value for this resistor, and also a current direction which is consistent with my chosen direction. Okay, let's say this is I2, this is I3, and I can also give some arbitrary I1 in this direction. Then I should have some V1 associated with this. Okay, so basically we can simply write down KVL in this mesh. We have two meshes, as you can see. If I go in this direction, I can easily write one simple fact. Since I'm rotating in the opposite direction with respect to the given voltage, as you know, when I'm rotating, I come to the negative terminal first, so I have to write minus 120 volts. Okay, and then since I'm rotating in the same direction as the 8 ohm resistor, which is V3, plus V3 equals to 0. This is my first equation from KVL at loop 1. Let's say this is loop 1, first loop or first mesh. So from here I can see that the V3 should also be 120 volts. Okay, and since I know the resistance value, the R3 is equals to 8 ohms, I can use this information to conclude that my I3 should be V3 over R3, which is going to be 120 volts over 8, and that would make 15 amps. So I have found my I3. From here I can also use the Ohm's law again to calculate R2, because as you know, the V2 is 120 volts given to us, and it should be equal to I2 times R2, which is 24 ohms. Okay, from here I2 can be calculated as 120 over 24, which is 5 amps. Okay, so I have also calculated the I3 and I2, and at these, let's say this is node A and this is node B. Okay, and I can write down a KCL at node B. Okay, the current, unknown current I1 is entering there, so since it's entering, I will put a negative sign, and the two currents I2 and I3 are leaving it, so they should have positive signs. Okay, it goes to 0. From here I see that I1 equals to I2 plus I3. Since I know both of the values, then I can calculate I1. Then 15 amps plus 5 amps would give me 20 amps. Okay, now I know that the I1 is 20 amps, and I know, if I know the V1, then I can actually calculate, and I can use a second KVL around this second loop. Okay, this is the second loop, same direction. Since I'm rotating clockwise and I encounter minus sign first, if I write my KVL at second loop, it's going to be minus 200 volts of this voltage source. Okay, plus V1, because I'm rotating in the same direction, reference directions are same, and since I also rotate in the same direction as this, R2, I know its voltage value, so I can directly write down it as is 120 volts, and I complete my loop. I start from here and I end up here, so this should be equal to 0. So from here I can see that the V1 is actually 80 volts. Okay. Now I have previously found the I1, and I have also found the V1, so I can use the Ohm's law to calculate the unknown value of R, which should be V1 over I1. So 80 volts over 20 amps would give me 4 ohms. So the unknown resistance is found as 4 ohms. Let us continue with the next slide. Okay. We are given some measurement results, and from these measurement results we are supposed to create a model for this unknown device. The terminal voltage and terminal current were measured and shown as in the table. Using these values, we will first create a mathematical expression, then try to find out an appropriate circuit model for this. Okay, so what I do is I draw a voltage versus current graph. So I start with putting the numbers for the voltage and the current. Okay, when the current is 0, I have 25 volts. So this is where the point is 25, and this is 20 and 15 and 10 and 5. So when the current is 0, I have this, and when the current is, let's say, 0.1, and there is the 0.2, and there is 0.25. This is amps, and this is volts. I just mark my points. So this is the 15 volts range, and this is the 5 volts range. So my first point is here, my second point is something like this. Okay, I have another point which would give me this, and I have 0. So it's apparent that using these points, I can write down an equation of a line equation that passes connects all these points. So if you do the math, you can see that the V should be 25 minus 100i. Okay, this is the equation for this line. So knowing this, I can calculate the equivalent resistance seen towards the device, because I know that the R should be equal to delta V over delta I, which is basically the slope of this line. So taking points like, let's say, 25, so I can easily write down 0.25 minus 0 endpoints. So from here I get 100 ohms. Okay, 100 ohms as my equivalent resistance. And when I look at the circuit data, I observe that when the current is 0, the voltage is 25 volts, as you can see from the graph. So when there is no current flowing out of the circuitry or into circuitry, I can measure 25 volts, which means that I shall have a 25 volt source inside, and I have already calculated the equivalent resistance of it as well. So from here I can create a rough model for this device. So I have a voltage source, and I have a series connected resistor which is 100 ohms, and this is 25 volts, and this defines the VT basically. Okay, so in part B, using this model, can we predict the power that the device will deliver to a 25 ohm resistor? Okay, now in part B, we have our circuit, okay, which we can use this model to predict its behavior. This is our 100 ohms and 25 volts. Now these are the terminals, and I connect an load resistor of value 25 ohms here, and I want to calculate the power delivered to this. So I can simply write down a KVL around this. I'm assuming that the current will be flowing in this direction and in this directions for these resistors. Okay, since I'm seeing the negative terminal of the voltage source, I will start with minus 20, these are ohms, volts. Okay, and plus let's say I have an I1 current, and this is R1 and this is R2, let's say. Okay, I know that it's going to be I1 times 100 ohms and plus the same current I1 times 25 ohms. This should make 0. I'm writing the KVL. Okay, the reason is that the current has to be the same. There is no other path that the current can flow, so you can write the KCL here at this node, but it's gonna be like unnecessary. We can see it directly. So from here I can calculate the loop current as 25 over 125, which gives me 0.2 amps. Okay, now since this same current flows through the 25 ohms resistance, I can simply use I square R to calculate the current value. So the PRL, which is the load resistance that I connected to it, should be I square R, so 0.2 to the square times 25 would give me 1 watt. Okay, and last but not the least, in the very end, this time we are asked to construct a circuit model which uses an ideal current source and the resistor. Okay, again, it's possible because the same equation can be obtained. If we pull the current, then we can simply write down the line equation. We can rewrite the line equation as in this case it's going to be I equals to 0.25 minus 0.01 volts. Okay, I can easily construct it from the line equation, and from there I know that I can simply put or calculate the R value again, which is going to be the same because the slope of the line will not change. Our data is constant, so that we will have the same data, and using the basic relationship from the endpoints where the line intersects with the axis, we see that 25 over 25 over let me see. Okay. 0.25 minus 0 would give me 100 ohms again. But this time, since we have an current source to use in order to model this behavior, this resistor would be in parallel. Okay, so my model in this case using the current source will be something like this. And now I have my modeling resistor, which is the equivalent resistor. Okay, that's a resistor of 100 ohms, and I have the value of 0.25 amps, because when my my voltage is 0, the current value is 0.25. So this would give me the model. So I have the VT again here. Now if I connect the load resistor to it, let's say in part B I have these my model, okay, I have these my device, I have my resistor here, 100 ohms, and I have the load resistance of 25 ohms connected here, 0.25 amps going in. So I just need to use the basic Ohm's law to be able to write down the KCL. If you write down the KVLs, you see that the voltage across there will be some current flowing in this direction. So the voltage across the load should be the VT. Then I can write down the current of the load using the Ohm's law. And I also know that there will be some current flowing in this direction, and I also have this. So I can write down a KCL equation at node A. Let's say this is node A. So if I write the KCL at node A, I'm going to get, since I'm entering the node with the current source, I will have minus 0.25 amps. Okay. And when I'm exiting the node, I know that the VT is across the both resistors. So I'm going to get VT over 100 ohms plus the same VT over 25 ohms. And this will make 0, because all the currents at this node, the sum of the currents at node A should be 0. So since we have only one unknown VT, if you solve this equation, we are going to get 5 VT equals to 25. So from here we obtain VT as 5 volts. Now since I know the voltage value across this load resistor, I can calculate my P as VT square over R. Sorry for that. VT square over R load, which makes 25 over 25, and it gives me 1 watt again. As you can see, the circuit behavior, even though we use different approaches to model the unknown circuit, we obtained the same consistent results out of it. So this is a black box, and inside the black box I can model it as this. This is the first alternative, let's say, or I can model it this way. But as long as I stick with the circuit theory fundamentals, they behave the same. They give the same results for the same load externally connected to this. So this is basically the power of modeling. We can model unknown circuits using the basic elements that we have learned so far, and then we can further predict their future behavior based on the established mathematical model. Let us continue with the next example. Okay. In example 7, use Kirchhoff's laws and Ohm's law to find the voltage as shown in this figure. Show that your solution is consistent with the constraint that total power developed by the circuit equals to the total power dissipated as expected. So in this circuit we have two loops basically, and the current in the first loop, let's say this is the first loop and this is the second loop, controls the voltage source, dependent voltage source on the second loop. Okay, so I can write down a KVL in the first loop. Okay, KVL, let's say 1, and if I rotate in this direction, it's going to be minus 10 volts plus 6 ohms times IS. This is my controlling current, should be equal to 0. From here I can easily calculate that IS should be equal to 10 over 6 amps. Okay, and in the second loop, if I do the KVL 2, this is going to be the same thing, but this time I have the dependent source, so I'm going to write minus 3 times IS plus here, since I have a assigned direction, it means I'm going to get this, and VO is already given like this, so the current should be flowing in this direction, and I have the IO. So since I'm rotating in the same direction with the reference, so it's going to be a positive sign, then the IO times 2 plus IO times 3. Now, since I know the IS value, I can substitute it here in the equation. This is also should be equal to 0. So this is going to be minus 5 plus 5 IO should be 0. From here, IO is, sorry, sometimes IO equals to 1 amps. So I know the current flowing in this loop is 1 amp. So I can easily calculate all the powers because I know all the voltages and the currents right now. So the output voltage should be equals to 3 ohms times IO, which will give me 3 volts. Okay. This is the solution for A, and in part B, we first need to calculate the total power delivered to the circuit. So we separate the sources. Here I have an independent voltage source. Let's say PS should be equal to VS times IS, and for the given reference directions, I know that I'm going to get a negative value. The voltage value is 10 volts, but the current value should be minus 10 over 6 amps, which would, translate into 16.7 watts. This is negative, so it means my source is providing power. Also, for the second dependent, voltage source, I have VD times, let's say, IO, because IO current is flowing and it's again in the negative direction, so its value will be negative, and I know that the VD equals to 3 times IS, which is 5 volts. We have already found it. Okay. So I simply plug in my values. 5 times minus 1 amp, because IO is 1 amp, I0. I'm going to get minus 5 watts. So if I combine them, my delivered power is like power, power of total sources. is given as minus 21.7 watts. Okay, it's supposed to be consumed by the rest of the circuit. So let us see if that's consistent. First of all, I have the first resistor here, the 6 ohms resistor. Let's say this is resistor 1, so it's gonna be I can easily calculate it since I know the currents Is squared times R1. Then from here 10 over 6 squared times 6 would give me 16.7 watts. And in the second part of the circuitry, the passive component, let's say R2, 2 ohms resistor, the same applies there. IO squared times R2 would give me 2 watts positive power, and P3 would be I0 squared times R3, which will give me 3 watts. And if I add these things, I'm going to get a positive 21.7 watts consumed. So this is the total power of the resistors. So as you can see, the total power in the circuitry should be the total PS plus the total PR, which would make it 0, as you can see. So the solution is consistent with the conservation of energy. Let us continue with the next example. Okay. Now, in this particular question, we are asked to find the solution for a circuit model given for a transistor. Basically, it's a bit of advanced circuitry, but we will see that we can solve this. So assume that the values of the R1, R2, RC, RE, VCC, and VO are known. Okay, these are our known variables. Let us develop the equations that need to determine the current in each element of this circuitry. If you examine the circuitry, the variables written in blue arrows are the unknowns. So we have 6 unknowns. Okay, our unknowns are I1, I2, IC, IE, and ICC. Okay, so we have to solve them. In order to solve them, we need equations. So we can construct those equations using the Kirchhoff's current law, and also using the already given relationships like the relationship of the dependent current source. So if you look at the circuit nodes A and B and C and D, we can write down equations at these points. Okay, so let's say we write down an equation for at node A. At node A, I'm applying the KCL. I can write down that since I1 is coming in this direction, okay, I have the ICC here and I have IC. It means that I1 plus IC minus ICC should be equal to 0. This is my first equation from point A. Okay. At point B, I can again write down an equation here. As you can see, I have 3 currents and they have to sum up to 0 according to KCL. So all the currents leaving the node are taken as positive, and the entering currents are taken as the positive negative sign. So here I will have a negative I1 and positive I2. That would give me 0. Okay, this is my second equation. And at circuit node 3, at this point, if I again apply the KCL, in this case I have IE leaving that node, which has a positive sign, minus IC, it's entering the that node, and I also have the minus IB as it enters the node, which should be equal to 0. So this is my third equation. I also have another equation. If you look at the dependent current source, we know that the current flowing in this direction is IC, but IC equals to some beta times IB. So this is the fourth auxiliary equation that's coming from the definition of the element, the dependent source. So I can also use the KVL to construct additional two equations, because since I have 6 unknowns, I need to obtain 6 equations to be able to solve the circuit uniquely. We need to choose 2 closed paths in order to use the Kirchhoff's voltage law. Okay. Now, since the voltage across the dependent source is unknown, you cannot directly determine it from the beta times IB value. So we must select 2 closed paths that do not contain it, because its value is currently unknown. So if we simply choose this mesh, okay, we can achieve it. Okay, we can achieve it. So if we simply write down the KVL, okay, if I write the KVL at loop 1, let's say this is the loop 1, according to the KVL I can write down this equation. V0, I'm rotating in the same direction, its references are same, so it has positive sign, okay, plus, now the current is flowing in this direction, so it's gonna be IE times RE, okay, and since I'm now rotating in the reverse direction at this point, I'm going to get a negative sign for I2 times R2, should be equaling to 0. I can also take the large loop around the power supply. Let me show it. This is the loop that I'm interested in, okay, the outer loop, and I can again rotate in that loop. Let me write it outside so that you don't get confused. This is gonna be the second loop. It doesn't contain the dependent current source, so I don't have to deal with its unknown voltage. So the KVL2 can be written, since I'm rotating in the same direction as the VCC, this is fine. Now I'm rotating in the reverse direction with respect to I2. It's going to be I2 times R2 and minus I1 times R1, and I complete my loop. Because of this, I can obtain these as the fifth and the sixth equations. Now what we can do is, actually we have completed the basic requirements for solving these 6 unknowns. I have 6 unknowns and I have 6 equations, so this system has one unique solution. Okay. For the part B, to get a single equation for IB in terms of the known circuit variables, you can simply solve equation, I will roughly write it, okay, solve the 6, okay, get I1 from here, and then substitute this value into equation 2, okay, and solve this transformed equation, okay, transformed equation that you have already done, and from here you get the I2 and you substitute into equation 5, so that we can further solve this transformed equation for IE, and then I can substitute IE into equation 3, and if I use the fourth equation that I developed from the dependent current source, use the fourth equation to eliminate the IC. IC of equation 3. Then if you solve the transformed equation 3 for IB, you will get something like this, okay? VCC times this is a kind of mathematical exercise that I leave to you, but when you do it correctly you should have these results. R1 plus R2 minus V0, okay, this is all in one equation over R1 R2 over R1 plus R2. This is basically parallel equivalent of the R1 and R2, plus 1 plus beta times, this is beta, times RE, okay. This is the general equation for obtaining the IB value, and if you follow this, flow of, solution, you will get to this result eventually. Let us continue with the next example. Okay, for the circuit shown in find the current I1 in microamps and find the voltage V in volts and the total power generated and absorbed. So here we can simply take a look at the circuit. We have two meshes and we have an I1 current flowing in a certain direction, so I can simply denote that direction. And I have a voltage value here, and the current is flowing towards this let's say node C. Let's say this is A, B, C, okay, this is A, this is B, D and E. These are the circuit nodes, the connections in the components, okay. Here I know that there is some current enforced into this direction, so there will be some current flowing here, like the 30 I1, and I also have a current flowing in this direction with the value of I1. So actually, if I choose a reference direction like this, which will be same as two currents are approaching, it has to flow through the 6K resistor. I can simply write down a KCL at node C, okay. In this case, since I'm approaching with negative sign, I will use a negative sign, minus I1 minus 30 I1 plus the I resistor 6K should be 0. From here I can conclude that the IR should have a value of 31 I1s, okay. This is something useful for me because the total sum of currents at circuit node C should be 0. I use this fact to obtain my relationship for the IR. This is IR, okay. Now there are two meshes, as you can see in the circuit. Okay, and I can also write down a KVL, okay, around the first loop. So the total voltage drop should be 0. So I'm rotating in clockwise direction. Then I can simply write minus 5 volts plus 54k times I1, okay, plus so there is also this voltage source there, which is in reverse direction to my rotation. I encounter the negative sign first, so I put negative 1 volts, okay, and plus, if you multiply the resistance of 6 kilo ohms with 31 I1, you can obtain 186k I1s, and this should sum up to 0 because I completed my loop. Okay, now as you can see, the only unknown is I1 because k means 10 to the 3. So if we do the math here, I1 can be calculated, okay, as 6 volts over 54,000 plus 186,000, which will give me 25 times 10 to the minus 6 amps, which is basically 25 microamps. So I have found I1. Okay, good news. Now once I know the I1, actually I know all the currents through these components. In order to be able to calculate the power values, like I need to know the voltage across this dependent voltage source. Okay, this 30I1 thing. However, in order to find it, I need a second KVL loop, so that I can simply find a solution. So if I clockwise direction, if I apply my KVL, okay, KVL at second loop, okay, the total voltage drop should be equal to 0. Now I'm rotating in this direction. The voltage, unknown voltage, is positive, so I take it as is. Then since the reference direction in the 1.8 kilo ohms resistor is opposing me, it has to be negative sign. So if I simply write down the voltage drop values, calculate the voltage drop values, 64 I1, and there is the 8 volts which is in the same direction that I'm rotating, so I take it as is. And then there is the voltage drop over the 6k resistor, which will be 186k I1. So that will in total make 0. Okay, again, using this, and I know the value of the I1, so I know that the I1 equals to 25 microamps. Using a scientific calculator, I can easily obtain my voltage value as minus 2 volts. So now I know the voltage across this component as minus 2 volts, which means that it's opposing the reference direction that is given to me. I can calculate all the powers, but when we are calculating powers, let us first calculate the power that are delivered by the voltage sources. So P delivered would be the 5 volt source times I1. Okay, 5. Of course, since the current for all sources will be opposing their reference direction, I'm going to get a negative sign at the very beginning. So I put it at the beginning and write down this, 5 times I1. so it's gonna be 5 times 25 microamps, okay, plus for the 1 volt source, I have 1 volt times 25 micro, and for the dependent source I have minus 2 volts times 30 I1s, okay, so it makes 775 microamps, okay. And for the 8 volt independent source I have the same amount, 775 microamps. Now if you do the math, at the end we obtain minus 6150 microwatts. This is delivered power, okay. This is for solution of B, sorry, C. So this is part B and this is part A. And for the D, we need to calculate the total power absorbed. So we look at the components that consume the power, which are the resistor values, okay. So if we calculate the consumed power, we know that it's gonna be a positive sign because it's all the resistors. So let's say I have 64K times 25 microamps plus 186K times again 25 microamps plus 1.8K times 775 microamps, which is 30 I1. In this case, the total consumed power can be calculated as 6150 microwatts. For sanity check, we know that the total power should be 0 and total power delivered plus total power consumed will result in 0, which means that we have successfully or correctly solved the circuit, okay. This much currents are consumed and delivered energy or the power should be equal in accordance with the conservation of energy. So we have solved the question successfully. Let us continue with the next examples. Okay, now we have a new circuit here. In the circuit there is a current called I5, which is given as 2 amps. So we are supposed to calculate the value of the Vs and the power absorbed by this independent voltage source. In this particular example, the voltage source is absorbing the power, not providing. The power delivered by the independent current source, 5 amps current source, and the power delivered by the controlled current source, and the total power. Now if we before starting we need to denote the direction. So there should be a positive and negative polarity here. So the same voltage should be across the dependent voltage source. So here we have the, let's say, Vi. This is a current source, so it should be consistent. Then we know that there's 2 amps flowing in this direction, okay. So we can see that actually the Vi should be equal to 60 volts because they are in parallel, so we can directly say it. Now in the second part we also have some reference directions here enforced, okay. This is 4 amps because it's 2 phi, and if the phi is 2 amps then this is gonna be 4 amps, okay, flowing in that direction. So the current will come to this point, and then I choose, since the voltage source polarities are given, and we also know that it's absorbing power, so the current should be in this direction, not it's not sourcing, it's absorbing, so the IV should be in this direction. Okay, then I suspect that I can choose this kind of reference direction for the 10 ohm resistor. Okay, now what we can do is there are 3 meshes, and the first 2 ones are easy. Let's say this is the mesh 1, this is mesh 2, and this is mesh 3. I will start with mesh 2, and I can arbitrarily choose any direction. So up to now we have always used the clockwise direction. Let's use the anti-clockwise direction. So I will rotate in this anti-clockwise direction. Okay, now since I see the negative sign of my Vs, if I say KVL at around 2, the total voltage should be equal to 0. Voltage drop, sum of their voltage drops for all components. So I'm just applying the Kirchhoff's voltage law. Minus Vs. Since I'm rotating towards this direction, the 10 ohm resistor should have a positive value. Okay. Then I will have the current value times the 10 ohm there, and I can also see that since I can also write down the equation in such a way that we can find the current for this 10 ohm resistor. Basically, if you take a look, there is 5 amps going in, and there is 2 amps here. Okay, there is 4 amps moving in, and there is the unknown current for the 10 ohm resistor. Let's say it's IR. So at this circuit node A, if I apply first KCL, because I need to find that current. Okay, so let me correct. Let us start with the KCL at the first circuit node. So with KCL at node A, I see that minus 5 plus 2 plus 4 and minus IR should be 0. From here, it's easy to see that IR should be 1 amp. Okay, so for the KVL around the second loop, it should be rewritten. I can simply write down the minus Vs plus 1 amp times 10 ohms. Okay, and since I'm rotating towards 30 ohms, I'm rotating in the same direction, so I will add that thing too. And the current for the that resistor is 2 amps, so 2 times 30 ohms would give me Vs as 70 volts. Okay, so I have calculated the value of the Vs. This is for part A. Now in part B, the power absorbed by the independent voltage source, well, it's easy. The power is always defined as Vs times the Is. So knowing the values, and I can easily see that the current flowing through the Is can be calculated using KCL at node B. Okay, KCL at B tells me that minus 4 amps plus 1 amps and plus Is should be 0. From here, Is is calculated as 3 amps. So since the Vs is 70 volts and the Is is 3 amps, I'm going to get 210 watts of power dissipated. If the current was in the opposite direction, it would be generating, but now because of the current value is positive and my reference direction is in line with it, so it means that at this time our voltage source is not sourcing, but it's consuming power. So the rest of the circuit is more powerful than this, and it's overdriving our voltage source basically. So the power delivered by the independent current source can also be calculated. At the very beginning I mentioned that the voltage of this current source can be calculated as is in parallel with the 30 ohm resistor. So it's gonna be 2 amps times 30 ohms, and it's gonna be 60 volts. And however, if you take a closer look, the voltage direction, chosen direction is, you know, opposite. So we have the 60 volts, but the current direction and the voltage direction are opposing each other. That's why this is a generating source, and the total power generated by this can be V times the I, and it's gonna be 60 times minus 5 amps. Here the minus 5 comes from the fact that the arrow you know, points upward, which opposes the voltage direction. Okay, because of that I have to put that minus sign, so we have minus 300 watts generated. Okay, so there is also another independent current source which we have, let's say I2 for it. Okay, and for that the same applies, the voltage time the current, and here its voltage value can be calculated because the voltage across the 10 ohm resistor will be equal to its voltage value. So it would give me 10 volts. Okay, actually it's gonna be minus 10 because as you can see, the voltage definition on the resistor and the voltage definition on the dependent current source are opposing each other, so I need a negative sign there. So it's gonna be 10 volts, because you can simply write down a loop. Basically you can write down a KVL in the first and the third loops to see that the voltage across these can be, you know, calculated. So if I just, you know, rotate the clockwise in those loops, so let's say I have KVL at 3, so I will have plus voltage source I2 plus IR times 10 ohm, which is like, I know that this is 1 amp, gonna be 0. And from here the VI2 should be equal to minus 10 volts, and from here I can calculate the PI as minus 10 volts times 4 amps, which would give me minus 40 watts. Again, this is generated because the voltage and the current are, you know, opposing each other, which means it's generating. And for the part D, power delivered by the controlled current source. Basically, actually, we have calculated this. So this is the, you know, part D, and the total power dissipated in two resistors can be calculated as the P30. Let's say for 30 ohm should be 2 amps times 30, which gives 60 watts dissipation. And for P10 it's 1 amp times 10 ohms, and it's gonna be 10 watts dissipated. So the total power in this case, P dissipated, is their sum, P10 plus P30, which would make 70 watts. But I think I made a mistake. The thing is, the voltage across the 30 ohm resistor is not 30, it's 60 volts. Okay, so the current times the voltage would make it 120 watts, and the same applies for this, but since the voltage across the 10 ohm resistor is 10, it's again 10, and in total we will get 130 130 watts of dissipated power. So this is the total power dissipated, and as you can see, the total generated power and the total dissipated power equals to 0. So this concludes the tutorial session. Thank you for your attendance. See you next time.